everyone. Our speaker today is Dr. Jianhua from Brookhaven National Laboratory, where he, on a 6-month visit, he actually works at Florida State University in Tallahassee. He began his career in atmospheric sciences at Nanjing University, where he did his bachelor's degree in meteorology. And for his graduate studies, he went to the Institute for Atmospheric Physics in Beijing, where he did both his master's and PhD degree, and his advisor there was the very famous Professor C.C. Ye, who visited Stony Brook also at least twice, I remember. And his PhD degree was on simulation of land atmosphere processes in global models. So after his PhD, Jianhua went to the University of Hawaii as a postdoc, and then to Florida State University in Tallahassee, where he is now a research scientist. So and he has actually worked in several different areas very effectively and published papers in them. One of them I already mentioned in vegetation-atmosphere interaction, simulation of hemisphere complex process, and then he has published several papers in ocean dynamic simulation, the influence of topography and eddy mixing in the oceans. And then he has done very interesting and original work on heat bias processes in the atmosphere, or in climate, I should say. So that is his topic. So that is what we are.
Thank you, Sultan. And I also want to thank Steve because I had a similar talk in BNL. Then Steve would welcome me to Sultan to have a seminar here. Basically, this talk is about some kind of unconventional view of the climatic feedbacks. But I'm not saying that this conventional view of the climate feedback is totally different from the conventional views. And also, we have basically it's developed from the conventional views. And so I want to mention this important work by Dr. Sayce in 1989. I think this may be the first comparison of the models about the climatic feedbacks. There are 14 AGCMs, and their interpretation of the cloud feedback. And at that time, the computer models is not so well developed yet, and it's very hard to have a long time integration of the model. So Dr. says they developed a very creative method by first changing the sea salt temperature, and then you look at you will induce a forcing. Then estimate the climatic feedback, and what they have found is that most of the variation in the climate sensitivity is related to the model's climate feedback. And they said in the paper, cloud feedback is dependent on all aspects of the model and not just on the cloud formation parameterizations. Now, there are also many other factors of the GCM, such as the hydro cycle, would play a dominant role in the models. So this like the you will see the climate sensitivity is like in these 40 models is between 0.4 to 1.1. If we use the CO2 forcing like 3.7 or 3.8 watt per square meter per K, and we can get climate sensitivity about 1.5 degree to 4.1 or degree for WCO2. So it's amazing, like this basically the similar result to the recent IPCC L4 or IPCC L5 estimate. Okay. Then just last Sunday, I read a sentence. I was very touched by this sentence, and I want to share, especially with the students here. It says in Chinese, 做音乐不可以不自在. I translate it into English is like, you should never do music without 自在 in your heart. So 自在 I translate this into English is like mental freedom or free will or like unbounded imagination. It's subtle in Chinese. Though why I want to mention this, because when we are okay, let me show you this about the 自在 I'll show you. We know this the very famous philosopher, Chinese philosopher Zhuangzi, in about 2,300 years ago. Is the beginning of his book. It said that in the northern deep, there is a great fish, thousands of miles long. It turns into a giant bird whose back is thousands of miles in size. When it gets aroused and takes to flight, its wings are like clouds covering the sky. So that's kind of unbounded imagination. What's amazing is that when we are doing climate science, we can use this kind of imagination for this very complicated climate system. So we can imagine what will be the climate of Earth without a rotation. And we can ask, what would be the possible climate change if the Earth suddenly reduces its rotation rate by, say, 10%? We can use the first physical principles to imagine what will happen in this climate system. And that's the enjoyable side of being a scientist. Because, so, unbounded imagination about these unlimited possibilities, and just in our mind. Then, of course, we have to very hard working, and with a lot of mistakes and failures and maybe disappointment, and then suddenly maybe we can be rewarded with an aha moment. Oh, I found something. That's amazing. Huh? Then, okay, this the story. What I want to talk about this talk is about this aha moment. And I want to mention first, this is because of the collaboration with Dr. Ming Kai in FSU. And he initiated this work, and he, in fact, developed a prototype of this framework. And in 2005, Dr. Ming Kai, he want to explain why we know that global warming is larger in the polar region. And usually we will think, oh, because if there is ice feedback, so the warming there should be larger. But he developed a very simple model. It's just 4 boxes. This is for the tropics surface or the ocean, and this is the tropic atmosphere. This is a high latitude atmosphere, and this is a high latitude ocean or the surface. So there is the transport from the tropics to the high latitude, and this A is the air temperature, G is the surface temperature. So it's very simple, just 4 variables. And in this model, there is no ice albedo feedback. And he found in this 4-box model, we can get a larger polar warming in the high latitude, even there is no ice feedback. But of course, people will say, oh, this is too simple, it's not the real Earth. So then eventually we develop a very idealized GCM by using a real GCM basically based on Gamow model. And then we use the real radiative model, and then I developed a surface model and the radiative adjustment. Then basically we can constitute an idealized Earth system. Then we try to also find the polar warming, but at that time we do not know how to represent this method. We tried many different awkward ways, like using a shadow model when we are running this model different, to fix the transport from the tropics to the high latitude. And then suddenly one day, it's just before the Chinese New Year of 2007, this aha moment that come to my mind, thinking that basically the energy balance not only holds for the TOA, the top of atmosphere, or for the surface, but also for any location. In the model, it's like any grid point at any longitude, latitude, altitude. And I just squared on the papers different boxes from the top the model to the surface, and then each grid, this box, there is energy balance. Of course, this energy balance is not just the radiative energy balance. It's the balance between the radiation and also by the dynamics heat transport. And then the second, I realized that the equation of this balance is well described by the equation for the total energy conservation equation. We know that equation very well for any student for atmosphere science or ocean science. So why not we just directly use this equation, not using the TOA balance? And then the third one is, okay, the surface temperature and atmosphere change will induce a long wave radiative cooling. This radiative cooling can represent a matrix. Later in the paper, we called it the Planck feedback matrix. And this matrix will never be a degenerate matrix because the cooling, when you change the temperature at the local, it will cause a cooling. But at the upper layers, other layers will cause a very weak heating, radiative heating. So basically, this matrix will never be degenerated. It's very safe to use. Okay. So then we also realized that the TOA radial balance we usually use in the traditional climate feedback analysis is just the vertical, the integrated version of the total energy equation, conservation equation. And then we also realized, oh, in fact, this method we have used that in the two-box model. But because there were only two variables, we did not want to use any of the result of this equation, use any method. But in fact, this method is inside this model. Before we go to this new framework, I want to first review the basic concept of climate feedback usually used in the since 1980s. A lot of papers like by Hansen in 1984, and also by the book of Paxton and Ott. And so the concept is like that. If there is the input, and for the system you will have initial gain, then you will have induced some outputs. Then these outputs will have a feedback system. They will have feedback induce further input to this system. So then you will get this feedback system. This is the gain, and this is the input, and this is output, and this is the so-called feedback parameters, and this is the G0 is the initial gains. And I will not go deep into the details of this framework. It's well known for any feedback system. Now for the climate, okay, we can see if there is a forcing that is induced by the solar radiation, the change in the solar radiation or change in the CO2, you will see a radial forcing at the top of the atmosphere. Then will induce a change in the surface temperature. Then this change in the surface temperature will induce the albedo change because the ice will change, and then water vapor will induce further radiative fluxes. And then we know that the vertical distribution of the temperature will also be changed. So there is a lapse rate feedback. Then also, of course, there the cloud, the change in the cloud. So it's like this, but we know that this in equilibrium state, basically the TOA still need a balance. So we got this surface temperature, and this is the initial gains by the just the surface temperature change, and this is the other feedbacks. Exactly same as the conceptual in this figure. And this is by I think it's in IPCC I think in L4. estimate of the feedbacks by different different authors from different models. Thornton and Hild in 2006, and other Coleman in 2003. This is the water vapor feedback. It's very strong positive feedback. And then we can see the cloud feedback here. It's a very large model into the model spread. And then this the albedo feedback is relatively smaller, but is positive. And this is a negative lapse rate feedback. If we add this water vapor feedback and lapse rate together, we will see a positive feedback and with a smaller model spread, and this total response. Now, we can see some main merits of this framework. First, this framework basically reflects the fact that the temperature of this Earth system, or the surface atmospheric temperatures at first order, is determined by the radiative balance between incoming solar radiation and outgoing long-wave radiation. In fact, is the case for the global mean temperature. And secondly, it's very concise. The overall property of this coupled system can be the feedback system can be represented by 5 feedback parameters, which can be compared among different models and compared with the observations. And also, it may provide a picture of climate change may be easily understandable to the general public, but also easily misunderstandable to the general public, because in fact we know that the climate system is not very just so simple a vertical with a vertical temperature and the radiative balance between the incoming energy input and the outgoing energy.
Could you clarify on the first bullet? You've got the word to first order.
First,
what do you mean? I mean, there are other things like sensitivity flux, late heat flux.
Yeah, I will using some imagine the thought experiment. If like we just change the rotation rate of the Earth, there's totally nothing changing in the TOA radiative balance. And we know that with the change of the rotation rate, then the Rossby wave and the heat transport from the tropics to the high latitude will be changed. And we can imagine how large will be global mean surface temperature will be changed in this case. In this case, there is no TOA balance, the TOA forcing. I believe there will be some change in the global surface temperature, but not very large. That because we have this. If you change it, in fact, it's very easy to using an idealized coupled simulation. You can see this case. You have changed the heat transport, then the cloud, the distribution will be changed. Then the water vapor will also be changed, and then the ice will be changed. All these feedbacks will happen without any radiative balance. So that means the surface temperature or global mean temperature is not just determined by the radiative balance, and only at first order it is. That's why the conventional framework can be used, because at the first order it is the case, but not exactly the case. Yeah. Okay, we can ask some questions from this view of the climate system and the climate feedback. First, why is the change in the surface temperature is chosen as the output and the control variable in this climate the feedback system? Is it just the physically more important than other variables in this system, or just because we live at land surface, we care more about this land surface? We just care more about the surface temperature change than the change in the other. Then, how about if the giant bird and the fish are mentioned in John's book, if they have their own climate model, would they also care more about the temperature in the atmosphere or just in the surface in the sea, not to care about the surface temperature? And then, why are the changes in the water vapor and in lapse rate and cloud is induced by the surface temperature? Is there some kind of cause or effect relationship with these variables. Are they really induced by surface temperature change? We know that in the climate feedback analysis, this is the climate feedback induced. X is represent the cloud or water vapor, lapse rate, or albedo. We can use partial X, partial TS. Implicitly, we are assuming these changes are caused by surface temperature. But really, are they there? Is maybe just a kind of scaling between the X and the TS. It's not the cause and effect. And I will show, in fact, there are many changes in the X. It's not caused by temperature, surface temperature change. And then we can further ask the question, why does the radiative forcing have to be at the TOA? Then another question, so we know this is radiative balance. Where is the rule of the dynamics? You will not see any rule of the dynamics in this radiative balance because it's just disappeared where it is. So here comes in my mind there are some limitations of the above mentioned framework. First, there's some kind of arbitrariness in this framework. There are many different ways to define the radiative forcing and the feedback parameters. And in fact, it does cause some confusion in the literature. Now, secondly, there are only radiative processes are explicitly considered. All of important dynamic processes, in fact, I will show that they are lumped into the lapse rate feedback. And therefore, because of this, the interconnection between the physical processes that may be broken in this framework and may be distorted. For example, if we consider the rule of the dynamic in this framework, the dynamics are in the stratosphere, you cannot represent in this framework. And then if we are concerned about the regional climate, then this framework must be misleading because it's not locally or regionally. It's not just the balance between the incoming radiative forcing and outgoing long wave radiation. It's the balance between incoming solar radiation and the radiative balance, and also the change in the energy dynamic heat transport. It's the three-term balance. It's not just this radiative balance. So now we'll look at the CO2 forcing. And also I will take a look at the so-called fast tropospheric adjustment found by Gregory and Webb in 2008. So the question is, the forcing, why has to be at a TOA? In fact, there are two aspects of the radiative forcing. The first is the total amount if the TOA. In fact, it is a vertical mass weighted integration of radiative heating from the surface of TOA, which this is exactly if you integrate radiative heating in the atmosphere from a surface, you will get the surface radiative flux. Now, secondly, there is a vertical structure in the radiative forcing. This is the radiative forcing. If you can take a typical vertical structure of the temperature in the atmosphere and the water vapor, do not consider the cloud first. It's the clear sky. If you run the radiative transfer model, you will see at each layer will induce a downward long wave radiation. At this layer, about 600 is downward radiation is about 5 to 6 watt per square meter. And if you're going up to the top of atmosphere, it's about 2 watt per square meter. And there is a vertical structure. It's each layer, this is a downward radiation. And we know that in the troposphere, in stratosphere, the radiative balance mainly is decided by the radiative balance. So you will see that maybe in 20 days we will see a change in the temperature, because in this area this flux means here is the divergence of the downward radiation flux, means basically in the stratosphere it's a cooling, CO2 cause the cooling in the stratosphere. So they will induce the cooling, the reducing temperature in the stratosphere. Then you can make adjustments after the balance. In 20 days you will be balanced. Then you see the radiative balance in this way. Again, you can see the downward radiative flux in this. That means CO2 forcing can cause a lower troposphere and a surface heating. And then in the middle tropospheric, it's a cooling effect. And then going to upper troposphere, again, it's a heating. This is the vertical structure. But if you look at just the TOA, it's just this value. Here, because it's more than 5, or about 5 water per square meter, because it's a clear sky. It's larger than the estimate in the IPCC report. In IPCC report, it's about 4 or 7 or 3.8 or 3.7 water per square meter. It's like this. We only cared about this, but I would say this is in fact important. Why? Let's go. Okay, if we look at the global, it's like this. The heating in this region and the cooling, CO2 causes the middle tropospheric cooling, and then heating in the lower stratosphere and cooling again. And if you look at the TOA, it's like this. And if you look at the surface, it's like this one. And if you look at the heating for the whole column of atmosphere, it's like this from the polar region to the tropics. Now we can look at the tropospheric adjustment. Why there is such a tropospheric adjustment very fast? In fact, in the models, in several days, less than 20 days, this adjustment will happen. In fact, at this time, because of the large heat content of the ocean, basically there is no surface change. And they found in the models there is a significant rapid tropospheric adjustment to the cloud CO2, leading to a change in the cloud without change in the surface temperature. That means large part of the cloud change in the models is not induced by the surface temperature change. And this reduces the effective radiative forcing, which is similar to the indirect and the same direct effects of aerosol. So they called this adjustment in the radiative forcing. But we can think about why would this happen. We just imagine another different kind of forcing. Similar to TOA is 4 water per meter square, but all these forcing just happen at the surface. Basically, if there is no heating in the atmosphere, then this rapid adjustment will never happen, because only this forcing, the effect will happen until the surface temperature changes. But because of this, this is their estimate for different models. And because of this heating in the atmosphere and in it's a vertical structure, if you run a GCM, atmospheric GCM, with just like m per run, you put this forcing into the model, then you fix the surface temperature. You will immediately see in like 1 day or in several hours, we will see the system will be changing. The cloud will be changing. In water vapor will be changing. The lapse rate will be changing. All this will happen because of this is just the response of this vertical structure of the forcing in the atmosphere. And in fact, Kami and Watanabe, they did this experiment and published in Climate Dynamics in 2013. It's just they use 4 CO2 in 3 hours, basically no response for the temperature, and in 1 day you can see warming here. There's basically no warming at the surface, but there are warming in the lower troposphere. And then in 5 days you can see huge warming in this region. And then this is the equilibrium run for it's like several years you can get this equilibrium response. But this is the faster response. Is it a feedback or just a response? I would say it's a feedback, because if we look at the feedback, is not necessarily induced by the surface temperature. It is a feedback induced by forcing. That's right. And then also the change in the cloud. In 3 hours, you can reduce a cloud in this region. And then in 1 day, 5 days, and the equilibrium response, you can see a lot of response in the cloud is happened in just in 5 days without any change in the surface temperature. So now I just introduced the vertical structure, the forcing. How can we incorporate this vertical structural forcing into the climate feedback analysis? So first, we want to define the climate forcing. It's more than just a radial balance perturbation at the TOA. The forcing has a vertical structure and also a horizontal structure. And it is the heating or the cooling perturbation with a three-dimensional structure that causes climate change. Accordingly, the climate feedbacks, we can define the different ways. It's the energy transfer or the transport perturbations due to the change in the water vapor, the cloud in the surface albedo, and also this flux change induced by the response in the atmospheric or oceanic motion. These are dynamic feedbacks. All these will respond to the initial external force, and they will return to a new equilibrium state. Then how to include this? Then we, as I mentioned before, the TOA feedback framework, these all the local and non-local dynamic feedbacks, they have the lumped into the lapse feedback. And we can explicitly include this dynamic process into the climate feedback analysis, because the TOA radial balance is just the vertical integration of the total energy conservation equation. That means we can directly use the total energy conservation to analyze the climate feedbacks. This is what we developed, the different, we call the climate feedback response analysis method. This is vertical is a different model layers in the atmosphere, from the top of atmosphere to the lowest model layer, and this is the surface. And you can see it's the land surface or the ocean, the whole column energy balance of the ocean. So this is long wave radiative cooling. This is short wave radiative heating, and these turbulent fluxes, and these convective fluxes, and these large scale fluxes, vertical and horizontal, and they also the friction in the models, because we have the diffusion in the models. And then we can see a perturbation of this equation induced by the forcing. This the forcing has a vertical structure as shown for the CO2 forcing. You can also use the other forcings for the like solar radiation forcing and any kind of. Yeah. Then you can get this long wave radiation change due to changing the temperature, the changing the because of the water vapor, and then the cloud. There's the long wave part, and this is the short wave part, and this is the matrix I named is the radiative cooling caused by the temperature. It's a matrix we call the Planck feedback matrix. And I will show what's like. This is when we publish paper, we just have this figure. No other calculation made to submit a paper. It's based on the vertical structural temperature and the water vapor. You can get positive part in the diagonal. This because of you at each layer you have suppose 1 degree temperature will induce radiative cooling here in the middle, and then other layers will cause radiative heating, but much smaller. So this is the TOA, and this is the surface, and this matrix, it means each volume. That means the temperature change at each layer caused the radiative heating perturbation in each different layers. So this method, by using this matrix, we can decompose the temperature change induced all these energy fluxes. This is caused by external forcing. There's albedo feedback, and there's water. This cloud feedback, and this is water feedback, and also this dynamic process. And then add them together, you will get a total temperature change. This is decomposed of the climate sensitivity. I want to note this method. If we just for this matrix, if we vertically integrate of this each column of this matrix, then we will lead to the radiative kernel developed by Soden and Held. And we also further integration for different layers, you will reduce to the TOA balance. Because I have mentioned that it perturb the total energy balance conservation if you integrate from surface to the atom, top of atmosphere, exactly is the TOA energy radiative balance equation. So now I want to use a very idealized model. I mentioned it's a kind of Earth climate system. There is no hydrocycle, but there is a water vapor change, and basically follow, because we know that the relative humidity in the climate change basically fixed. So we can make this idealized climate system by using dynamic cold and radiative cold, and then the surface cold, slab ocean, and the adjustment of convective adjustment. This is the basic the mean climate. It's similar. This is the Earth climate. Okay, the temperature is about very similar to the real Earth, and this is the water vapor, and this is the jet stream, similar to what we have observed. And this is from the GFDR model. We use the fixed relative humidity in this simulation. Now, this is the climate change induced by doubling CO2. This is the atmosphere change. We can see in this model there is no albedo feedback. There's just no albedo. And we know that the radial forcing of CO2 is larger in the tropics. But the warming, surface warming, this is surface warming, and this atmosphere warming, basically is larger in the polar region. And we can compare this pattern with the simulation in IPCC report, basically similar polar warming application, but the troposphere warming is smaller, because in our model there basically is no moist convection. We have just the convective adjustment is basically the dry. We have no hydrocycle in our model. So now what I want to do is just decompose this climate sensitivity in different terms from the different contributions. We know this is the climate forcing, WCO2, and at the surface, and we can, if suppose there's no other change, just this forcing, only balance this forcing by the radiative, long wave radiative induced by temperature change, then the temperature change in this way. Larger at the lower troposphere, and they are cooling in the polar troposphere, and then heating and the cooling in this way. Then add the water vapor feedback. This is the water vapor feedback, the heating in the atmosphere. You can induce heating here, then cooling here. And this is the TOA balance. And this is the surface balance, is induced by water vapor feedback, water vapor change. And this is the total atmosphere heating or cooling induced by the change in the water vapor. And then the response of temperature should be in this way. I have some more say about the water vapor feedback. We know that if we look at the TOA balance, the contribution of water vapor feedback is from the upper layer water vapor. Then I would ask if the change in the lower troposphere water vapor important to the water vapor feedback. I did some calculation, this based on the GFDR model. You can see this is a net downward radiation induced by the water vapor change at 200 millibar, basically the TOA balance. And this part is caused by the water vapor change above 700 millibar. So basically, the TOA balance is mainly caused the upper layer water vapor change. And the lower water vapor very little contribution to the TOA balance. But if you look at the surface radiative balance, the upper layer water vapor contribute very little, but mainly contribute from the lower water vapor, low layer water vapor change induce the downward long wave radiation at the surface. Why is it important? This will cause the different response in the hydro cycle, because we know that the change in the precipitation or hydro cycle has to be balanced the radiative cooling in the atmosphere. If there's only the change in the upper layer water vapor, we know that basically will induce a net heating in the atmosphere, because larger it at the top in the 200 millibar, but very small at the surface. So this shows a net heating of atmosphere. Then we will imagine a reduced hydro cycle associated with this water vapor feedback. But if we consider the lower layer water vapor feedback, then the change in the hydro cycle will be totally different. Okay, we will go back to the change in the model. This is the surface flux change, and this is the friction change, and this is the induced the energy flux from lower troposphere to the upper troposphere by convection. And this is the unit water per square meter per 100 millibar. It's a heating and a cooling here. And this is the largest scale horizontal heat transport. We can see basically there is induced larger polar heat transport from the tropics to the polar region. Even in this case, we know that the warming at the polar region is larger, so there's reduction in the polar and tropics temperature, surface temperature difference. But the heat transport is increased, not decreased. So this is the TOA balance. We will see total TOA imbalance in this way, and this is the, if we integrate from surface to the top of atmosphere, this is the total heat transport, and these two, add them together, almost exactly zero. That means it's TOA imbalance is just should be balanced by the heat transport. Now, what will be the temperature change caused by these energy perturbations? This is the surface, surface temperature change, and this atmosphere temperature change induced by this pattern in local dynamics, mainly the vertical convection. Lower in the tropics, there will be cooling in the upper troposphere heating because of the enhanced convection, and then larger scale dynamics will induce this kind of change. Polar warming is larger, and the tropics is cooling, and this way. You can see the difference in between is about 1 degree between the polar and the tropics. And for large scale, it's about 0.5 to 0.7 degrees. Now, we can add them together. This part is the forcing, the temperature change due to forcing and water vapor feedback. Okay, we will if there is no dynamics transport, we will imagine a larger warming in the tropics and a larger warming in the lower troposphere in the tropics. But these dynamics will reduce the warming in the tropics at the surface, and enhance the warming at the polar region, and also reduce the warming in the lower troposphere, but enhance the warming in the upper troposphere. If we add them together, these two together, is just exactly what we have seen, this pattern, the warming pattern. the black curve is the original simulated. The red curve is the sum of this C-frame decomposition. And this the shading is the original simulated climate change, and it is the counter is the sum of this decomposition. Okay, this model is still idealized. It's not exactly the real.
Yeah, I still have a question about why there's no tropospheric warming, more enhanced tropospheric warming here. Because if your adjustment is along a more radiative band, then you would see it.
Yeah, the adjustment here, because we use some called dry adjustment, not exactly the moist adjustment.
Okay,
so
you have a constant lapse rate.
Yeah. But I will show this method using the real climate models.
Yeah, okay.
It's not my work. It's by Dr. Minkai and his collaborator, just published in Climate Dynamics, and also there another paper in Journal of Climate. This is for the CCM3. The shading is the original warming pattern, and the counter is the decomposed temperature change, and sum them together, and basically the exact same. And and this one is for the Japanese miracle model. We just use the annual mean. This is just for 3 months because this method can be used in the different months. Because we know that the energy conservation equation basically can be applied to monthly time scale or seasonal time scale because of the very small heat capacity of the atmosphere. So this is for the fall season in the miracle model, a different version of the model. The shading, the original simulated climate change, and the counters are the sum of the decomposition. Is C-frame decomposition. So you can get a very good, decomposition of the climate sensitivity by this method. This is by Japanese scientist Yoshimori, published in Journal of Climate this year. So the summary: there are merits and limitations of TOA-based climate feedback frameworks. And a new framework, C-frame, is based on total energy conservation in the coupled atmosphere and ocean and surface system. And we should remember that the climate feedback or sensitivity analysis in this idealized coupled 3D GCM and even the fully coupled models, we can see the relative role of the thermodynamic feedbacks and the dynamic feedbacks, how they are shaping the pattern of the climate change. So I'm not saying they are totally contradictory with the traditional way, but they are complementary. We can provide a different perspective of the climate change and their mechanism. Okay, thank you very much for your time and questions. Yeah.
Yes, very interesting. So, as you actually commented on this, you found decreased surface temperature gradient.
Yeah.
But you still find increased energy transport. Have you? So in your model, do you have?
Yes.
More. You also have latent heat transport.
There's no
There's no latent.
Latent heat, but because of there are two things. If there is latent heat transport, then basically, as similar to other GCMs, they will reduce of the dry static energy transport forward. Basically, it will be reduced. But the total energy transport, the moist static energy must be increasing. Then, if in this model there is no latent heat transport, then the total energy must be increased. The transport must be increasing because of the property of this radiative balance. And in fact, I did not analyze in detail. I just think about this question. Even at the surface or near surface, temperature gradient is reduced, but in fact, in the upper layers, the temperature gradient is enhanced. And what that means, in this case, the we know that the forward heat transfer mainly by the eddies. That's why the bioclinical eddies. In this case, there is no topography, so there is no stationary wave. In this case, in fact, we will imagine the property of the bioclinical eddies in global warming is changing. The vortex structure and the heat transport property will be changing. But I don't know exactly what's the mechanism yet.
Yeah, it would be interesting to actually diagnose it more carefully about what eddies are.
Yeah.
What will happen if you allow the ocean to do the heat transport?
Yeah.
How is it going to change?
Yeah. Okay. In fact, in this framework, the ocean transport can be included because the equation you can see the equation for the surface. You can exactly apply it to the ocean, but it's not just the surface; it's the vertical integration of the ocean transport. If there is like feedback from ocean transport, then what my experience with the real current model is like if you have enhanced the heat transport in the ocean, then basically first you will see a reduced atmospheric heat transport. So the net effect is maybe the pattern will be changed, but not we do not know exactly what will happen. But I have seen in the like CCM3 models, if you have enhanced heat transport like the positive phase of AMOC, then basically the reduced heat transport, then the polar warming you have different structure. Different phases of AMOC, you will see different response in the climate. Yeah.
Okay, there are no more questions, so let us thank our speakers for
Thank you.
Okay, so very basic. I know it's kind of so I've got not of a little bit. So I feel which I can using and then software might turn